Hello, today we will treat the topic of wind power and the energy conversion that takes place during this process through which different turbines take advantage of the kinetic energy from the wind and are able to convert it into useful power, which in this case will be electricity. Now we move forward to our first question. First question being for paper 1, where we read: a wind turbine produces power P when the speed is V. Assuming that the efficiency of the turbine is constant, the best estimate for the power produced with the wind speed when the wind speed becomes 2V is. First of all, we have to highlight the key elements within the question, which include the power P, the speed V, and the thing that the question asks us to find, which is the best estimate for the power produced when the wind speed becomes 2 times the wind speed. First of all, as we know that in theory doubling the wind turbine area doubles the power extracted, we already have a point to make in how we could solve the question. So right from this point we could say that answer A could be possible, but let's see why it's incorrect. In theory, it can be said that doubling the wind turbine area will double the power extracted, but unfortunately, this answer cannot be, because there is more to it than just doubling the power produced, where it's not only being 1 to 2, but rather there's another ratio that will be that doubling the wind speed increases the power by a factor of 8, meaning that there will be a ratio of 1 to 4, and this will make that doubling the wind speed will make our answer not be 2p, but rather it will be 8p. It couldn't be 4p. 4p could only be possible if the wind speed was constant, was already v, and 6p does not make any type of sense in relation to what the question asks us. Alright, that's for paper 1. Now we move on to paper 2, where we read that the question treats that we have air of density rho and speed of v passes through an area A. The question is, deduce that the kinetic energy of the air passing through the area per unit time is given by the expression 1/2 rho times the area times v cubed. What actually the expression wants us to tell, kinetic energy per unit time, is the same thing as power. In order to show the kinetic energy per unit time, first, to make it a little bit clearer, we will draw the turbine that we have, the turbine. So we have here the 3 blades, and a small area within the blades is described as the area. So we will label it, and then in order to have a volume, since we have a V cubed, we will have to draw a column of air that passes through the turbine, and then we can get an expression for the volume. And then, so we have here that our expression is equal to V, volume is equal to the area of the blade, times this distance. But in order to get this distance, we can just see that it's the wind that's moving through the turbine with a velocity v per unit time. So as a result, the distance, this distance that we showed previously, is not going to equal d, but rather will equal v times t, and our equation will be v equals a times v, which is for speed, and t, let's note that this is for volume, so let's make it a little bit bigger. You may ask yourself, why are we getting the volume? We're getting the volume in order to get mass, in order to get the kinetic energy. And in order to get the mass, we will write it down. We will say that mass is equal to the density times the volume, which will be this letter rho. So we will put rho times the volume, which is capital, so we don't get confused. And since we add a rho to one side, we have to add it to the other, so it will be rho A V T. Now that we have the mass included within our equation, we can put the formula for kinetic energy. So kinetic energy is equal to 1/2 mv squared. And now we will substitute what we already have into this, the formula for kinetic energy, which will give us 1/2. The mass is rho A V T. We move downwards. We could move this a little bit over. Times V squared. Now, the next step is just simplifying, which we'll be able to do since this V and this V are the same, so now we will have V cubed, and the final answer will be just as what we originally saw, will be 1/2 F rho A third is equal to kinetic energy divided by T, as we want per unit time, and that will be our final answer. In this part, we will use the formula that we already have in a real scenario. So we read, air of constant density 1.2 kilogram per meter cubed is incident at a speed of 9 meters per second on the blades of a wind turbine. The turbine blades are each of length 7.5 meters. The air passes through the turbine without any change of direction, and immediately after passing through the blades, the speed of the air is 5 meters per second. In order to understand better, we should draw the problem and what they're telling us. So, we will draw the wind speed that's coming in through this end, the turbine blades, which are here, and the wind speed exiting. So we have 5 meters per second as the exiting, the 9 meters per second entering, and both of these are wind speed. Air has a constant density, and this density is 1.2 kilograms per meters cubed. Now, moving on to the questions that are being asked, we can see that what we're looking for is the total power, total sum of power, which would have a subtraction given that it's the initial power minus the final power. So the equation would be 1/2 the density, initial density, times the area times initial speed cubed minus 1/2 rho, which is the density final, times the area times the final speed cubed. We don't have the area, but we have a radius. So from having the radius, we can derive it and find the area, because area is equal to pi r squared. And now we can simplify the whole equation in order to find like terms. What does this mean? That we we'll bring down 1/2 is common in both, and pi r squared, and now we have parentheses, density 1, full speed 1 cubed, minus density final, or 2, speed final, and cubed, and this would be equal to 1/2 times pi times, let me get some more space here, times 7.5, which is the radius, times 1.2, which is the constant density, times 9 cubed, with here, let's move it right down here, let's shrink it a bit, 9 cubed minus 2.25 cubed, let's shrink that to, and not forget the parentheses here and here, and we punch this in into our handy calculator, which will give us a result of 53,000 watts. The next part is extremely simple, where we only have to analyze the fact that the electrical power generated is based upon the overall efficiency, and also of the previous answer that we already got, which was 53,000 watts of the power extracted from the air. This is pretty simple, so we just put power is equal to the 72%, so we put 0.72 times 53,000, and this would equal 38,000 watts, and that will be our final answer.